Stochastic column row method for traveling salesman problem, the Dhouib Matrix-TSP2. Abstract: in this paper, a stochastic method, named Dhouib Matrix-TSP2, is designed and developed to solve the traveling salesman problem. This method based on our last column row. The stochastic process generates the shortest total transport distance. Keywords: combinatory optimization, meta-heuristic, column row method, stochastic. Introduction. Recently in Dhouib 2021, we developed a new constructive method named Dhouib Matrix-TSP1 in order to quickly find the optimal or near optimal solution for the traveling salesman problem, TSP. This method, Dhouib Matrix-TSP1, is a deterministic algorithm. Whereas, in this paper, we present the Dhouib Matrix-TSP2, which is a stochastic version of Dhouib Matrix-TSP1. This stochastic technique is used as a way to diversify the research space. Hence, this process will allow to generate different realizable solutions. The outlines of the paper are as follow. In section 2, the traveling salesman problem is described. In section 3, the Dhouib Matrix-TSP1 is presented. In section 4, a new stochastic column row algorithm, Dhouib Matrix-TSP2, to find optimal or near optimal solution for the TSP is depicted. In section 5, the application of our proposed method on a 10A10 distance matrix is provided. Finally, concluding remarks are given in section 6. Traveling salesman problem. In the traveling salesman problem, the aim is to find the shortest round trip. This latter is essentially a Hamiltonian tour, where a set of cities are visited only once except the starting city, which will be also the ending one. The traveling salesman problem is NP hard. However, it is easily formulated as NN. In the literature, there are several research works interested in solving the TSP. Mehmet and Kalasai 2021, applies the variable neighborhood search algorithm to optimize the cost-balanced TSP. Saji and Barkatu, 2021, designs a BAT meta-heuristic to solve the TSP. Christoph and Ursula, 2020, solves the asymmetric traveling salesman problem using the pheromone-based harmony search meta-heuristic. Akanksha and Sharma, 2019, uses the particle swarm optimization algorithm to solve the TSP. Todosijvik et al., 2017, develops a variable neighborhood search meta-heuristic to optimize the TSP. Dhouib Matrix-TSP1. In our previous research work, Dhouib 2021, we have presented the deterministic Dhouib Matrix-TSP1 method, which is composed of 4 easy phases, see Fig 1. The 4 phases of Dhouib Matrix-TSP1 are described as follow. At first, calculate the standard deviation for each row, then find the minimal element existing in the position dxy in the row of the smallest deviation. For more details see Dhouib 2021. Next, insert x and y cities in the list cycle _list and discard the columns of x and y. At second, compute the minimal element for row x and row y and select the smallest between them named z. At third, add z in the cycle _list and discard its column. Then, return to the last phase if there are still non-discarded columns in the matrix, unless, go to the next phase. Finally, transform the generated route in cycle _list to be a round trip, translate the cities in the beginning of the round trip at the end until the starting city will be at the first position. In addition, insert the starting city at the last position in the round trip. Dhouib Matrix-TSP2 design. This section will describe the proposed method, the Dhouib Matrix-TSP2. Actually, it is a stochastic version of the Dhouib Matrix-TSP1. Whereas, the selection of the minimal element is replaced by the random selection from k minimal elements, this will enhance the diversification of the research space. The pseudocode of the proposed approach, Dhouib Matrix-TSP2, is presented as follow. See Fig 2. Well, to quickly and effectively search the optimal path for the 10 cities of the traveling salesman problem, we first apply the Dhouib Matrix-TSP1, which needs only 10 iterations. Finally, we need to transform the generated tour 5-1-710324896 to a round trip by translating the cities in the first position to the end until the starting city will be at the first position and add the starting city at the last position 171032489651. So, using the Dhouib Matrix-TSP1, we found 2.78211, deviation of 3.17%, in only 10 iterations using the standard deviation metric, see Fig 14. When we insert the Dhouib Matrix-TSP2 in an iterative structure, it can easily find the optimal solution, 2.69646. In Fig 15, we can see the step-by-step generation of the optimal solution using Dhouib Matrix-TSP2. Conclusion. This paper aims to insert a stochastic process in a deterministic optimization method, Dhouib Matrix-TSP1, in order to generate the new method, Dhouib Matrix-TSP2. The distinguishing feature of this new technique resides in the random selection of the n smallest elements which force the fetch of new solutions, not simply sought the smallest value as in Dhouib Matrix-TSP1. This new stochastic method is developed using Python language and the final test result proves its effectiveness and good convergence. In our future research works, larger scale TSP will be explored through our new method Dhouib Matrix-TSP2 to search the optimal path.